Lab 4, DC and RC circuits. So we first began the lab by using a virtual circuit to represent and predict and also quantify the behavior of a circuit with resistors in series and parallel. We examined the behavior of capacitors and resistors. So the main physical principles we used are the loop rule, which is how the potential differences around a circuit equal zero when you add them up, energy conservation, which is delta V capacitor plus delta V resistor equals zero, and then how delta V equals Q over C, and then Ohm's law, which is I equals B over R. Then we had to predict the two currents, I1 and I2, because the two batteries have 1.5 volts each. In total, it's 3 volts. So we know the resistors are, because they're in series, we can add them up and we get a total resistance of 147. So I is going to be 3 volts over 147 ohms, and that's 0.0204 amps. And we know I1 equals I2. Then I simulated a circuit in the CCK. So the readings for the currents I1 and I2 matched the prediction of 0.02 amps. And then when we had to switch an ammeter backwards, it would still measure the same current. We then replaced an ammeter with a voltmeter, and the voltmeter read 3 volts, which is just the voltage of the two batteries and the voltage drop of the circuit. However, the ammeter measures 0 amps because the circuit is enclosed, and the voltmeter has very high resistance, which means there's no current running through the amp meter. We then measured the potential differences at different locations, and there's a drop from the batteries of negative 3 volts. And then we have across the 47 ohm resistor a change of 0.959 volts, and then the other resistor has a change of 2.041 volts. These findings lead to the total voltage, so the loop rule, and when we add up the differences, we get 0 volt. Here we have a graph of the potential versus circuit position, and we know how there's an increase from A to B of 3 volts, and then we have a decrease of until 2.041, and that corresponds to a 47 ohm resistor, and then we also decrease from there to 0, and that corresponds to our 100 ohm resistor. So including the voltmeter doesn't change the ammeter readings because the ammeter only depends on the resistor and the voltage, and a well-designed voltmeter doesn't draw any current from the circuit as it has a high resistance. The voltmeter connected across in 100, the ammeter still measures 0.02 amps. However, when we do connect an ammeter in parallel with the 100 ohm resistor, the ammeter readings change to 0.06 amps, and this is because the current takes the path of least resistance, so it doesn't go through the 100 ohm resistor, and this causes the overall resistance in the circuit to only be 47 ohms. As well, we know that the perfectly designed ammeter has no resistance. Then I calculated the resistance across each element, so the 47 ohm resistor, we just get the change in voltage divided by the current, and we get 47.95 ohms. For the 100 ohm resistor, we get 102.05, and then for the wire and ammeter, we get 0 ohms, which is what we expect, as we expect them to have no internal resistance. So the light produced by a 10 ohm bulb, it starts off very bright and gets dimmer until the capacitor is fully charged, and then if it's also connected to the capacitor, it will start very bright and dim as time goes by. When we connected our circuit with a bulb and a capacitor, with the 10 ohm bulb, it took 8.7 seconds for the capacitor to charge and 10.63 to discharge, and the 20 ohm bulb, it took 17.93 seconds to charge and 22.37 seconds to discharge. Lastly, we did the time-dependent voltage. So we measured the voltage across the capacitor with a voltmeter, and we recorded 20 seconds of the voltage versus time data. So here I have the time and then the voltage across the capacitor, and then I have delta V over V naught, where V naught is just going to be the first reading, which is 9 volts, and then just take the natural log of that data. We know we get that the slope is going to be negative 1 over RC. So from this, I plotted the data, and I got, after putting into software, the slope is negative 0.167. So I know that the RC from my simulation is going to be negative 1 over negative 0.167, which is 5.988 ohms Farads. And then RC theoretical is going to be just 30 ohms times 0.2 farads, which is 6. And our values are very, very close. So if we did the lab in real life, the actual ammeter won't have a 0 ohm internal resistance. However, it will have very low resistance, but it will still influence the voltage running through the circuit by affecting the current flowing through it. So our readings won't be the same. So if we did the lab in real life, my prediction would be that the capacitor would take longer to charge than in the ideal model. And this might be because the resistance in the wire for the real model might not be equal to 0 ohms. So this means that the more resistance, the longer the capacitor takes to charge. As well, the battery might have some internal resistance as well. Thank you for watching.